Alright guys, so we are going to continue today. We're still actually on section 1. We didn't finish last time. We kind of just went to halfway of 4.1. And the reason why I did that is because I wanted to make sure that you absolutely understood radians before we got to this part. Okay? Because in my opinion, as far as 4.1, this is the more complicated part of it. Okay? Now that we all understand what a radian is, now we can actually use radians for what we're going to do today. So, like I said earlier, we're going to be talking about this whole concept of speed, okay? And we're going to talk about linear speed and angular speed. Okay, that's really the two topics that we're going to discuss today. All right. So we had this conversation earlier that we have these objects that are traveling in circular motion, right? So they're traveling in this circular path, and we're going to measure the speed. So then my question to you is, if they're going on a circular path, why in the world am I finding something that's linear? Why would it be a linear speed if I'm going on a circular path? Any thoughts? Okay, so you're saying, well, technically, yes, you're not going in a line, but, I mean, I wouldn't call it not a dramatic change, but technically you are eventually making a dramatic change in directions. Good thought, though. What you guys got back there? What's up? Constant speed. So I said it was traveling at a constant speed. But why would I call it linear speed if I'm going in a circular path? Okay. So when I grab the speed, even though I'm going on a circular path, do you guys agree that it's going to be linear? It's a linear speed. Furthermore, if I am traveling around in a circular path, isn't that like traveling the circumference? And we know that the units for circumference would be like meters, inches, etc., etc. It's a linear measurement. In other words, I could take that circle and flatten it out and make it into a line, per se. So even though we're traveling in a circular path, their speed would be linear. Are you okay with that? Good. Alright, so here's my question. So because we are on this circular path, you guys told me when I ask you, the first thing you say, when I say, what speed? All of you guys jumped up and said, distance over time. That's what most of you guys said right away. Agreed? And I was like, fantastic, I agree with you. Speed is the distance over time, right? We're going to improve that definition for our purposes because we're going on a circular path. We're going to say that linear speed, well, if I'm talking about a distance in a circle, I'm talking about circumference, right? But what if you don't actually go the entire circumference? What if you only go part of the circumference? What do you call that? We learned it last time. So if it's only part of the circumference. Not a sector. Arc length. It's an arc. Right? It's only arc, it's only part of it. You're thinking sector, you're thinking area. So right now we're just focusing on the circumference. So if we're only going on part of the circle, we don't have the entire circumference. We only have an arc of it. So how about we change it from distance to arc length over time. Are you guys okay with that? It's still the same concept, right? Well, can we furthermore improve this formula? Definitely. Because you know how to find arc length. How do I find arc length? In radians. In radians. Radius times your angle, theta, over time. So now I'm going to give you a shortcut, or basically, we don't like to write the entire word. We're lazy in math, so we use a symbol. Linear speed is a cursive L equals r theta over time. You have to memorize that formula. Okay? Linear speed is equal to r theta over time. Here's my question to you. You have a formula, and I'm sure you're going to be able to apply it. What does that formula help you find? Like if you were to explain to someone that's not taking this class, you'd be like, well, this formula helps you find this. What would you say? So we said linear speed, right? But they don't understand what speed is. So how fast what? Good. This formula helps you find out how fast an object is traveling. Okay? It doesn't say anything about directions, or we're not going to call it velocity, right? But at least you're going to know how fast it's going, right? Then we can improve this and talk about direction and whatnot, but you can take care of that in physics. Cool? Alright. We have linear speed. Now that tells us how fast something is traveling. Can we apply it? That's it. You ready? Okay. Example number 1. Pretend that you're in a Ferris wheel. So you're in a Ferris wheel, you and your friend, and let's say the Ferris wheel is rotating, so it rotates 3 times per minute. Okay? So you're on this Ferris wheel, and it takes 3 full rotations every 1 minute. Cool? You as a passenger, you are 24 feet away from the center. So passengers are 24 feet away from the center. So if you want to sketch a drawing, you're welcome to. You don't have to, but here's what we know so far. We know that if this is the center, and here's the passengers, we know that that's 24 feet. Agreed? And we know that it is rotating 3 times per minute, right? I'm not really going to include that on the drawing, but that's all I have so far. The question to you is, what is the linear speed of the passenger? Okay? And I'm going to be more specific. I want you to have your answer in feet per second. So we have a Ferris wheel. It rotates 3 times per minute. Passengers are 24 feet away from the center. What is the linear speed of the passenger in feet per second? So pretend you're the one riding this Ferris wheel. What would be your linear speed as you are traveling on that Ferris wheel? Okay? Alright. Any thoughts of how you would start this problem, or what we could do here? Yes, sir.
Find the circumference.
Find the circumference? Okay. And then what would you do with that?
Well, if it's going 3 times per minute, then I would say, okay, like, the circumference is 48 high.
Okay, so then...
So then I would say, like, in 20 seconds, the passenger travels 48.
Interesting. So you're going a different direction. So you're actually kind of analyzing this through and just kind of like use reasoning to answer the problem. You guys agree? He's like, okay, so I can find the circumference. Think about what you just learned today. Okay, I gave you a formula, right? Yes.
I would start with the formula to see what you
Good. Here's one strategy that I use for word problems. Okay, you don't have to do it. This is just my suggestion. I like to read the problem, and I like to focus on the final question, which is what I'm trying to answer. The final question is, what is the linear speed of the passenger? I like to always kind of underline or highlight because that's my goal. I'm looking for what? Linear speed. At that point, I totally agree. Linear speed, I'm like, wait a second, so how do you find linear speed? Well, we just learned that to find linear speed, it is r theta over time. So I like to write down the formula. Here's why I like to write down the formula. This is what I'm looking for. In order for me to find it, I need all this information. Then I have a starting point. Can you figure out what this is? Well, I'm going to go back to the problem. We'll start with the radius. Do we know our radius? 24 what? Feet. Awesome. Time. Do we know our time? 1 minute. Awesome. And lastly, I need to know my angle. Do I know my angle? What's that? That's a very good observation. So I didn't actually, but I told you that you're rotating 3 times. And we learned that one rotation is how many radians? 2 pi. So if you're rotating 3 times, how can you find out the angle? So there's 3 rotations times 2 pi per rotation. That means your angle is 6 pi. And so you're totally right. If you use degrees, you would do the same thing. But in order for you to use this formula, you're going to have to eventually turn back into radians. So might as well stay in radians. Okay? Now you have everything. You're good to go. We can answer this problem. Linear speed equals 24 times 6 pi all over 1. Now, before we actually do the computations, what would your final units be with these numbers? It would be feet per, is it second or minute? Minute, look, I have it in minutes. Okay? Now, that is what you would get with these numbers. However, it asks you to have it in what? Feet per second. We'll take care of that here in just a second, but can we figure this out at the moment? We sure can. 24 times 6 is what? 144, and then we have the pi, right? 144 pi over 1. So that means that my linear speed is 144 pi feet per minute. Technically, that's a correct answer. Agreed? I wouldn't say that there's anything wrong with that. The only thing is just make sure you meet the requirements of what units they're asking. And this is where the chemistry comes in, which is dimensional analysis. You guys remember that? Okay. So, we know that we have 144 pi feet per every 1 minute. Agreed? Now, dimensional analysis allows you to change units. Now, I want to keep the minutes, so I'm not going to change the minutes. All I want to change is the... No, actually, I want to change the minutes, right? I'm going to keep the feet. I want to change the minutes, right? So, I want to change it into what? Seconds. Remember that for dimensional analysis to work, you got to have the same unit on the bottom and on the top so that they can cancel. So that means that I need to put minutes up here. And seconds down here. Well, we know that 1 minute is equal to how many seconds? By doing that, guess what's happening? Look, that cancels away, right? So then I have 144 pi feet over 60 seconds. At this point, I have satisfied the units that they were asking me for. Simplify this out a little, okay? That means that your linear speed is going to be 44 and 60. I'm thinking 144, it's a perfect square, and it's 12, right? And then 12 times 5 gives you, okay, they're both divisible by 12. So 144 divided by 12 is 12, and 60 divided by 12 is, so your answer is 12 pi over 5 feet per second, and that will be your linear speed. Yes?
Why is that dimensional analysis now 1 minute?
This is a simple problem. I just want to show you the steps. We're going to get to a problem where you're going to have too much going on that you might want to kind of reserve your actual transformation of units until the end. I agree. I would have personally rather 1 minute. From there, I would have said 60 seconds and call it a day, right? I agree. I would not count you wrong for that. I just kind of wanted to show you that some of the problems are going to get complicated where you might want to keep an order of things so that you don't get lost within all the work. Cool? That's a very good thing to bring up, okay? Do we feel comfortable applying the formula then? Could you, if I asked you, this would be an exact answer, agreed? Could you turn that into a decimal and give me an approximation? Yes, you could, right? The units would still be feet per second. Agreed? Questions? Yes, sir. Yeah, I will specify. So if I say round to 3 decimal spots, then at that point you would plug it in and actually find out the decimal. If I don't say that, you can leave it like that. Cool? Alright, let's try one more problem. Alright, example number 2. A record player is turning at 45 RPM. Do we understand what RPM means? Revolutions per minute, rotations per minute, repeats per minute, same thing. Okay? So a record player is turning at 45 revolutions per minute. The distance from the center to the needle is 4 inches. Okay? Let me make sure. Do we all know what a record player is, by the way? Yes? Okay. Just making sure. I mean, just checking. What's up? The needle doesn't go all the way to the edge. Okay? So we have a record player, has 45 RPM. The distance from the center to the needle is 4 inches. Okay? The question is, find, and I'm going to use a symbol, linear speed of the point on the record when it began rotating. And I want your units to be in feet per minute. Let me make sure we all understand, because the question might get a little confusing. The needle is not the one that's rotating. You guys agree the needle is going to be stationary. It's that one point where it starts rotating, that one point. I'm trying to figure out what's the linear speed of that one point. Okay? Right? Because here's your needle, here's your record, that's where it's starting, then it starts to rotate and then it comes back, right? At that same spot. That's what I'm trying to figure out. What is the linear speed of that specific point as it rotates? Cool? Alright, so try it with your partner and then we'll come back and go over it together. Alright, I'm recording, guys. Okay, so here's what we know. We know we have to use this formula, so linear speed equals to r theta over time. I knew that my radius was in 4 inches. The time was 1 minute. And to find your theta, you needed to know the number of revolutions. So because you have 45 revolutions, and because you know each revolution is 2 pi radians, then if you start here and then you rotate, that's 2 pi, 4 pi, 6 pi, so on until you reach 45 revolutions. So instead of doing that, 45 times 2 pi gives you 90 pi. Cool? At that point, you have everything you need. So I did radius times theta over time, so that becomes 360 pi over 1, but my units at that point were in inches per minute. So then I had to change them to feet. 360 over 1, I multiply by 1 foot over 12 inches, right, because 1 foot is equivalent to 12 inches. The inches go away, and then you have 360 pi feet per 12 minutes, which narrows down to be 30 pi feet per minute. Questions? Yes? Sure. Let's pretend that this is your record. Okay? And just pretend, just for our class purposes, there's a needle, and then there's your needle right there from the center, just to make this problem easy. Cool? Awesome. Alright, any other questions over linear speed before we move on to our next concept? Are we okay? To find theta, you need to know your number of revolutions. I agree. Without knowing the number of revolutions, there's no way you can find your angle. Okay? Alright. If that's the case, then we're going to move on to our new topic, which is angular speed. Alright guys, I need you to pay attention to this, okay? I'm going to try to sketch this and it's going to be terrible, but bear with me, okay? So let's pretend we have a gear. You know what I'm talking about? Like a gear. That's terrible, but there it is. And then pretend you have a bigger one next to it. So something like that. It's a beautiful, beautiful gear right there. Okay? So in order for these gears to work, there needs to be a certain type of rotation. Otherwise, the mechanism will not work. Agreed? If this gear is rotating on that direction, how would the smaller gear be rotating?
The other.
Clockwise or counterclockwise? It has to go there. These two gears depend on each other, right? Because then this little teeth of the gear pushes the other one, making it rotate on that direction. They can't both be going on that direction. That's impossible. That mechanism would not work. Are we okay with that? Alright, so we have one smaller gear and you have a larger gear. My question to you is, we just learned about linear speeds. What could you tell me about their linear speeds? What do you think? Yes. So you're telling me that the linear speeds are going to be the same. Why? It's the same rate. They codepend on each other. If one of them is rotating at a certain linear speed, the other one has to be rotating at the exact same linear speed in order for this mechanism to work. So let's write that down first. In order for this to work, they must have the same linear speed. Okay? Agreed? But here's my question to you. This gear's rotating. Most people are going to tell me that the smaller gear is moving faster. Why would someone tell me that the smaller gear is faster than the bigger gear? Jay, what do you think? I'm sorry, can you say that one more time?
Because the radius of the smaller gear is smaller, it allows for better turns, so like the circle or the gear will have to spin faster before it.
Okay. Mary Rose, do you want to add something to that? That's what you were going to say? You got something to say?
Yeah, I was just going to say basically the way of saying that.
So because the radius is smaller, then most people are going to think at that point that this is going to be faster? Did I understood that correctly? Okay. Let's talk about rotations, because we're talking about angles. And we know that angles measure rotation, agreed? Well, how would you describe the relationship as far as rotation goes between the smaller gear and the larger gear? Lindsay, what you got?
The smaller gear would have more rotations per minute than the larger.
So you're saying that the smaller gear would have more rotations per minute. And typically when you visually see that, if you see something that is rotating more than the other, that makes you think like that's faster. Agreed? That has to be going faster. It's rotating more. That one's rotating less. The smaller gear has to be going faster. And I'm going to say, you know what? I agree with that person. This one's faster, but it all depends on what we're talking about. Their linear speed is the same, but they have another type of speed, something called an angular speed. We learned that angles measure rotations, and you just told me right now that the smaller gear is going to rotate a lot faster than it would the larger gear. So that means that the smaller gear has a greater angular speed than the larger gear. Can we all understand that? And it all has to do with the rotation. Okay? So, the smaller gear has greater RPM than larger gear. Nope. Therefore, it has a greater angular speed. So at this point, you must be asking, well, how in the world am I going to find angular speed? Okay, angular speed is found like this. Angular speed is equal to, well, let's pause. You told me that speed is what over what? Distance over time. If we're using angles rather than distance, we're going to use angle over time, which in our case then becomes theta over time. Okay? Now, we're too lazy to write that entire thing out, so we use W for angular speed. So W equals theta over time. You're going to have to memorize that formula as well. Can anybody tell me what the units would be for this formula? We're no longer using degrees anymore. We're using radians. So radians over whatever unit of time you have. So seconds, minutes, hours, days, years, whatever you want to use, right? So, but it's always going to be radians over some kind of unit of time. Okay? And before we go too far, can anybody tell me and explain, like, I don't know, a 7th grader, what does this formula help you find? What's up? No. Time. What do you guys think? Let's go back to, what does the word speed help us find? How fast. Okay, so this helps us find how fast what? What does that stand for? An angle is what? Rotating or changing. Alright. Angular speed is how fast an angle is changing. Do you guys see how in the small gear, your angle's changing a lot faster than on the larger gear? Cool? Alright. Then I got a problem for you. Do we all have this down before I move on? Awesome. Alright, so I'm going to give you a problem. Write it down. We all know that Earth rotates how many times per day on its axis? Okay, so we know that Earth rotates on its axis once per day. Find the angular speed of Earth in radians per minute. Cool? I'm going to repeat it one more time. We all know that Earth rotates on its axis once per day. Find the angular speed in radians per minute. Go. If you're watching the video, please check your answer. Okay. At this point, we've reached the last problem that we need to go over. This is, in my opinion, the most complicated problem that we're going to go over, and this will be very similar to something that you will encounter on either a quiz or a test. So I'm going to need you to pay attention. Okay? Alright, so no more questions on the Earth rotating. We're fine? Alright. Then here's a brand new problem. Pretend there is an 18-wheeler. Okay, so we've all seen an 18-wheeler. So we have an 18-wheeler. Excuse me. And let's say that that truck, we'll just call it a truck. And the wheels on the truck Go round and round. Okay. They have a diameter of 1.2 meters. Okay? So the truck has wheels that have a diameter of 1.2 meters. The truck travels at 72 kilometers per hour. Okay? Find angular speed of its wheels in radians per minute. Alright, so make sure you have the problem down. A truck has wheels of diameter 1.2 meters. The truck is traveling at 72 kilometers per hour. Find angular speed of its wheels in radians per minute. Okay? Alright guys, we're going to do this one together because I need to do it for the video, so sorry. Okay? We're going to do this one together. Okay? Todos juntos. There you go. Alright, here's my question to you guys. Remember the strategy that I told you to use? Always read the last question to know what you're finding. We're looking for what? I need to know what that is. So that means I need that formula. The formula for angular speed is what? Theta over time. That's the formula I need. So I need to find out what theta and what the time is. Let's start with what we know. Reading the problem, you should know what time is. What's the time? 1 hour. The question now becomes, what is theta? And looking at this problem compared to the ones that we previously worked on, what's missing from these problems that the other ones had? Well, it does have, technically you have your radius because you have the diameter. The number of rotations. All the other problems kept telling you this many rotations, this many RPM. This one doesn't. How did we use the rotations to help us out? Because if you had your rotations, you can multiply by what? To find theta. Agreed? So technically you're telling me that on all the other problems, if we knew the number of rotations, we could multiply by 2 pi. Agreed? But we don't have the number of rotations for this problem. So then we have a brand new problem. We need to find out the number of rotations. And that's become our new problem within this existing problem. We need to find the number of rotations. That's the challenge in this problem. Anyone have any thoughts or any ideas of how we can go about this? Drew, what you got, man?
We could divide 72 by 0.6, or
Okay, so I think you got the right idea. So he's saying, you know what? I'm going to take 72 and divide it by 0.6. Well, he's getting the 0.6 from the radius. Now, I think you have the right idea, but can someone help him improve that? Yes.
Find the circumference and then divide 72 by.
Okay, so now you're telling me that the number of rotations equals your total distance divided by circumference Do you guys agree with that? Well, let's talk about it. If you're traveling 72 kilometers, that means your tire is rotating a whole bunch of times, right, in those 72 kilometers. If we actually can find out the circumference of that tire, and then how many times that can go into that total distance traveled, we're going to figure out our number of rotations. And from there, we're set to go and solve this problem. Okay? Now, there's some other challenges we're going to have to encounter along the way. We can't apply this just yet. Okay? We need to find the circumference. So let's start there. So let's find circumference. Circumference equals what? 2 pi r, which in our case is going to be what? 1.2 pi. And the units will be what? Meters. Awesome. So I got my circumference. Now, I know my total distance is, oh, wait a second, we have a problem. 72 kilometers, and then this one's on, what am I going to have to do? Dimensional analysis, some conversions, okay? Does it matter if I turn the meters to kilometers or the kilometers to meters? No. I think it would be smarter here to turn the kilometers to meters, because otherwise it can get a little, like, the other way around might make the math a little bit more complicated, but it should still work. So what I'm going to do before I can actually find this out, I got to kind of go on the side one more time and turn those kilometers into meters, okay? So then I have 72 kilometers. So 1 kilometer is equal to how many meters? 1,000 meters. That goes away, so that becomes 72,000 meters. Whew. All right, can we find out the number of rotations now? All right, so now we're going to go back. Number of rotations equals total distance, in this case was 72,000 divided by what? 1.2 pi, and the meters are going to cancel out, right? Do you guys agree? Now, at this point, you could try to simplify this out. Agreed? So if you had a calculator, you could do it. But do you really have to? No. So here's what we know. That right here is our number of rotations. Do you guys agree? As it stands, it's the perfect, exact number of rotations. So now, if we go back, remember that theta is the number of rotations of 2 pi. So now we can find out what theta is. Theta equals number of rotations, which is this entire thing here, 72,000 over 1.2 pi times 2 pi. Are you okay if I write it as 2 pi over 1? The reason why I did that is because I want you to notice that what's going to happen with the pi? Goodbye. Now, 72,000 times 2 becomes 144,000. 144,000 over 1.2. Can somebody plug that in? What is it? 120,000? Okay, we've done a lot. What does this 120,000 represent? Not the number of rotations. Theta. And what are the units for theta? Radians. Oh, okay. All this work, and now we can finally go to the original question. Yay. The original question was angular speed, right? So now angular speed is equal to your radians divided by time. Well, time was in what? In hours, so 1 hour. And you're like, awesome, I found it. Did we meet the, oh, God, it wants it in radians per minute. Okay, so then we can divide by 60. You guys okay with that? So divide by 60, and then this becomes minutes. So then 120,000 divided by 60 becomes 2,000 radians per minute. And that was our angular speed. That was a lot of work, right? Alright, let's summarize the steps. You don't really have to do them, but we started out with just knowing the time and knowing the speed at which at the distance that it covered in an hour. We know that if we can find out the number of rotations and multiply by 2 pi, we can get the angle. So we need to find out the number of rotations. And the only way we can figure that out is if we have the total distance and we divide it by the circumference, right? If we find the circumference and then make sure that your units are the same, we can find the number of rotations. Then at that point, we can multiply by 2 pi to get our radians and finally apply the formula, okay? So it was a lot of steps. This will be on your test or quiz. Cool? All right, at this point, I'm going to give you a little break because you've been paying attention. We have one last concept to cover. It'll take me 5 minutes after that, okay? All right. We all know, for example, if I give you the following, I don't know, 175.25 degrees, right? That's something familiar to you. That's what you've been kind of exposed most of your lifetime as far as measurements and angles. Now, you discover in this class that there's other ways of measuring angles, which is called radians. And now you're discovering that there's a third method called DMS, degrees, minutes, and seconds. Okay? All right, let's talk about, because they're using units of time. It's kind of weird, right? You're using a unit of time to measure an angle. Well, let's talk about time for a moment. If I told you that last night I spent 1.5 hours studying, can you put that in terms of hours and minutes? 1 hour and what? 30 minutes. So typically, if we're talking about money and I say 1.5, you would say, oh, that's $1.50, right? It kind of goes along, right? But this 0.5, it doesn't match, right? It's half of an hour. It's 30 minutes. So we're going to keep that in mind, right? So here's what they do. You're going to have, and let me give you an example of what it would look like. This is not equivalent. I'm just going to make it up. 127 degrees, 13 minutes, 17 seconds. That's an example of an angle. 127 degrees, 13 minutes, and 17 seconds. So here's what they do, and it may sound silly, but there's a reason why they use it. I don't really know why they came up with this for longitude and latitude, because that's not really my area of study. But they came up with it for a reason. I'm not really sure why. But what they do is they take each degree and then divide it into minutes. So that means they divide it into 60 equal parts to find out how many minutes that is. And then they take every little minute and they divide it into another 60 to find out the seconds. That's all they're doing, okay? I wish I could show you that, but I'm not going to actually divide something into 60 twice, okay? But I'm going to show you how to convert between them, okay? So this means that you have an angle that's between 127 degrees and 128. It's not going to be more than that, and it's not going to be less than that, okay? Well, this is going to be 127 point something, and I'm going to help you figure out what it is. Well, this right here is a symbol for minutes, by the way, and this one is for seconds. We know that this is going to be between 127 and 128, so I'm going to say 127 point something, and I'm going to use parentheses, okay? Inside those parentheses, and I'm going to go one by one. Well, I have 13 minutes. How many minutes is there in an hour? So I'm going to write that as 13 over 60. Okay? Now, remember how I told you that they would take a degree and split it into 60 for 60 minutes? And then they would take a minute and split it into another 60 for the seconds? How many seconds is that total if we go back to the degree? Well, 60 times 60, which is 3,600. So I have 17 of those. So guess what? I'm going to have plus 17 of 3,600 seconds that are in 1 hour. Okay? Now, with your calculator, you're going to, don't plug this in. I only want you to find out what 13 over 60 plus 17 over 3,600 is. Someone try it, please. Okay. Almost no one has their calculator. 13 over 60, 13 over 60 plus 17 over 3,600. And I got that fraction, but I want it to be a decimal, so I'm going to hit math, decimal, enter. So guess what? That became 127.221 degrees. Now, do you guys recall that I told you that degrees are never exact? That's the reason why we use radians, they're more exact. Well, now we have three ways of measuring angles. Radians are the most exact, then DMS, And again, coming in last place is just degrees, because look, I'm going to have to round to give an approximate. Right? Okay. For time's sake, you're very lucky that you have this technology in front of you, because your calculator can actually do all this for you. You're going to have to know how to do it by hand too, though. Sorry. But let me show you how your calculator can work. Originally, we had 120. Here's what I'm going to do. I'm going to type 27. Now, I need to put the degree symbol. The degree symbol is under the angle menu. And the angle menu is located, you locate apps, you need your calculators. So you're just going to watch now because you're running out of time. Second apps gives you the angle menu. Look at the very first symbol there. Degrees. Bingo. And then I have what? 13 minutes, right? So I'm going to type 13. I'm going to go back into that menu. And option number 2 gives you the symbol for minutes. Cool. Lastly, I have 17 seconds. 17. Unfortunately for you, when you go to apps, you're not going to have a symbol for seconds. So I've seen people try to go and put 2 of this, and it doesn't work. Okay? So what you're going to have to do, there is a symbol for minutes, but for some reason it's not in there. So let me make sure I go back to there. It is located on the plus sign. Do you guys see the double? So you're going to have to do alpha and then the plus sign. There it is. 127 degrees, 13 minutes and 17 seconds. Hit enter. 127.221, which is what we found by hand. Okay? Be familiar with both, by hand and with the calculator. Okay? Now, that is if you take, this is DMS to degrees. Okay? What if we want to go backwards? What if I want to go from degree to DMS? And that's more like what I have here. So we have 175.25 degrees. Okay? If I'm going to DMS, you should already know the amount of degrees. What's the amount of degrees? 175 degrees. Now all I need to do is figure out the minutes and the seconds. Agreed? Okay. Notice how I only use the 175 and I have this 0.25. You're going to take that 0.25 and you're going to multiply by the number of minutes in 1 hour. Which is? Okay, so we're going to use our calculator. So 0.25 times 60, and that gives me 15. Guess what? 15 minutes. So this means that 175.25 is 175 degrees, 15 minutes. Think about time-wise. If I told you that I spent 0.25 of an hour, isn't that 15 minutes? Alright. Let's try another one. What if I have 332.54 degrees? Okay? We have the degrees already, right? 332. How am I going to find my minutes? 0.54 times 60. Agreed? So I'm going to say 0.54 times 60. And then I get 32.4. Uh-oh. That means I have 32 minutes. But notice how I had the 0.4. That means it's going to be in seconds. So I need to figure out what that would be in seconds. So you're going to take that 0.4 and multiply with how many seconds is there in a minute? Okay. 0.4 times 60. And I get 24. So that means there is what? Seconds. Easy enough? On the calculator is even easier. Are you ready? Check this out on the calculator. Originally I had 175.25. If I go back to that angle menu, look at option number 4. I'll repeat it again. So for the other one it was 332.54. I'm going to go back to that angle menu. Cool? Alright, that's all I got for you guys. Homework is actually located on the Learning Hub. I did not print it for you. It's in there. You can print it if you want to, or you can use your own paper. Cool?